this Stoichiometry and Chemical Equations Chapter 3 video, I will teach you about percent yield. So, when running reactions in real life, we almost always isolate less product than the amount that we should calculatedly obtain. In other words, reactions are never as efficient in real life as they should be on paper. We accordingly report something called a percent yield to quickly communicate how efficient a given reaction actually is in real life. So to determine a reaction's percent yield, 1. Use the method from my earlier video, linked to in the description below, to identify the reaction's limiting reactant. Remember, everything comes from the limiting reactant. The limiting reactant is crucial. 2. From that limiting reactant and, using the method discussed in another earlier video, linked to in the description below, identify the calculated moles of the product in your question. Now, this is that product's theoretical yield. 3. Plug the actual moles of this product, which will be given to you in your problem if you're working this out on an exam or a problem set or something, or you will obtain that actual number of moles when you run this reaction in real life in the lab. You take that actual number of moles and plug it into this equation. Percent yield is actual divided by theoretical times 100. Now, the best way for me to really teach you this in practice is to do an example. So when benzene, which has this formula, reacts with bromine, which has this formula, bromobenzene is obtained according to this equation. So here's our question. When 30 grams of benzene reacts with 65 grams of bromine, what's the theoretical yield of bromobenzene? And separately, if the actual yield of bromobenzene is 42.3 grams, in other words, you run this reaction in the lab and get only 42.3 grams of bromobenzene, then what is your percent yield? Now, if you want, you're welcome to try this on your own first, then hit play, and I'll show you how to do it on the board.
Whenever you're given a yield question, you always need to identify the limiting reactant. Now, sometimes the problem tells you which of the reactants is added in excess, and when that's the case, you don't have to go through the full BICPA process because you already know whichever one is the one that's not added in excess is the limiting reactant, okay? The excess reactant is the non-limiting reactant. Now, in a case like this where it tells us two different amounts, an amount of one reactant of the other, and we don't know which of them runs out first. That is, we don't know which one is the limiting reactant. We have to go through the full BICPA. So here's the process. Step 1, or step B of BICPA, is balance the chemical equation. Now, conveniently, this equation comes to us balanced. Now, if you need a review on how to balance equations, you can click the link supplied in the description below to watch a video on that subject. But we're done with letter B. Letter C stands for convert everything to moles. The reason is because whenever you're relating one of these substances to another, reactant to reactant, or reactant to product, or vice versa, you can only go through moles. In other words, moles and moles can directly touch each other, but grams of one thing and grams of another cannot. So moles are the intermediary between the two. Now, one thing that you can do is you can directly relate grams of one thing to moles of that same thing. But I cannot relate grams of one thing to moles of another, or grams of one thing to grams of another. Moles and moles can always touch. And I always think of like two moles on your skin touching each other because it's gross, but that visual helps me to remember that forever, okay? So we need to convert everything to moles. So I've got 30.0 grams of benzene. I'm going to lay down a set of parentheses using my unit analysis / unit conversion or dimensional analysis process. And in the denominator, the units are always going to be the units that were in the numerator of the previous term. So I'm going to put grams of benzene in the denominator. And is it possible to relate directly grams of benzene to moles of benzene? The answer is yes, because grams of one thing and moles of that same thing can touch. And that's what I mean when I'm talking about they can touch each other. What I mean is they can be put in the same set of parentheses, okay? So it is possible to directly relate moles of benzene to grams of benzene. How do you do that? Through the formula or molecular weight. So each carbon weighs 12 per carbon. I'm rounding, of course. The actual atomic weight of carbon is like 12.01 something or other, but I'm just trying to keep things simple. So each carbon weighs 12, and there are 6 carbons. 6 times 12 is 72. Each hydrogen weighs 1, and there are 6 hydrogens. So 6 times 1 is 6. So I've got 72 in the carbon plus 6 in the hydrogen. You add that together, 72 plus 6 comes to 78. So that is the molecular weight of benzene. So the grams cancel each other out, and I'm left with moles of benzene. When I plug that into my calculator, I get 0.385 moles of benzene. Now, you could round this to proper number of significant figures if you wanted. For right now, I'm not going to worry about that, okay? I'm just getting through the letter C, which is convert to moles. We'll now do the same thing for bromine. I have 65.0 grams of Br2. If you look on the periodic table, bromine's mass is around 80. Okay, and I'm rounding to simplify things, but again, the units in the denominator here are going to be the same as the units in the numerator up here, so they cancel each other out. Grams of bromine up top, grams of bromine down bottom, okay? So grams of bromine will be there. Is it possible to directly relate grams of bromine to moles of bromine? The answer is yes. 1 mole of bromine weighs a certain amount. Again, each bromine on the periodic table, its atomic weight is around 80. So if you have 2 bromines per molecule, it's 80 times 2 to get the molecular weight of a Br2. So that's going to be about 160. You'll notice that my units cancel each other out. I'm left with moles of Br2. I plug that into my calculator. I end up getting 0.406 moles of Br2. So I've now converted everything to moles, so I'm done with this letter C from BICPA. So I'm going to go ahead and clear the board to give us some room. In other words, what we just accomplished is we took these amounts in grams and converted them to moles. So we know that instead of 30 grams of benzene, it's really the same thing as 0.385 moles of benzene, and hopefully that looks like an 8. And we know that 65 grams of bromine is really 0.406 moles of bromine. Now, you might argue with me on the rounding for the significant figure rules. I'm going to kind of sweep that under the rug right now because we want to get through BICPA so that we can actually get to our answer. So the letter P in BICPA stands for pick one. That is, pick a reactant. And you can pick whichever one you like. At this stage, by the way, you might look at this and be able to quickly jump directly to the answer if you know what you're doing. And that's fine if you're in that position. But what I want to do is take you through the entire BICPA process, because I promise if you learn how to do the process and learn how to do it well, then you'll be able to get percent yield and theoretical yield questions correct 100% of the time, no matter how complicated they are. All the time, really easily, okay? So again, the letter P stands for pick one of these reagents. And you could do either one. You can pick the benzene or the bromine. I'm going to go ahead and pick the benzene if you're okay with that. Again, if you went through a subsequent process with the bromine, you'd get to the same eventual answer. So I'm done with letter P. Now the next question is ask or answer this question, okay? We have 0.385 moles of benzene. So the question that I ask is, based on how many moles of benzene I have, how many moles of bromine would I need? Okay? So based on the amount of moles of benzene that I have, how many moles of the other reagent, bromine, would I need? So I'm going to just write this down. Again, there's a 1-to-1 ratio here, stoichiometrically. In other words, there's an implied 1 coefficient here and 1 coefficient there, which means that if you have 1 mole of benzene, you need 1 mole of bromine. Or by analogy, if you have 0.385 moles of benzene, you need 0.385 moles of bromine. So if you can see that, then you don't have to go through the formal process I'm doing here, but I'm going to show you the formal process just so you know what I'm doing in case you're in a situation where you have coefficients here that are not 1-to-1, because sometimes that complicates things, right? So I've got 0.385 moles of benzene. How many moles of bromine would I need in order to react with 0.35 moles of benzene? Well, again, my units in the denominator here are going to be the same as the units in the numerator of the previous term. So I've got moles of benzene up here. I'm going to put moles of benzene in the denominator right there so they cancel each other out. Is it possible to directly relate moles of benzene to moles of bromine? In other words, can I put moles of benzene and moles of bromine in the same set of parentheses? In other words, can moles and moles touch? The answer is yes, yes. And that's what I mean when I say moles and moles can touch. They can be put in the same set of parentheses. Now, what numbers do I put in here? The numbers that you put in there are the coefficients. See, the coefficients in any balanced equation are the mole ratios between those substances. So here I've got a 1, and here I've got a 1, so it's a 1-to-1 ratio, obviously. But if this was a 2 and this was a 12 or something like that, I could put it in there and still do the math. Now, you'll notice that these cancel each other out, and I'm left with, multiplying this thing through, 0.35 moles of bromine. In other words, in this balanced equation, if I threw in 0.385 moles of benzene, I would need 0.385 moles of bromine to react completely with that amount of benzene. That is the first A, or the first ask/answer in BICPA. It is, based on the amount of moles I've got of this reactant that I picked, in letter P, how many moles of the other reactant would I need? And we now know. Okay, now we end with the last letter A. Do we have at least this much? The second letter A, by the way, does stand for answer the question. Do I have at least this many moles of bromine, of my other reactant? The answer is yes. I have 0.406 moles of bromine. Make sense? So I have extra bromine. So bromine is added in excess. In other words, because I have a slightly smaller amount of benzene, benzene's going to run out first because it's a 1-to-1 ratio between the two, so I've got excess bromine. So the whole process of BICPA doesn't get you to the final theoretical yield, it just identifies which of the reactants runs out first, i.e. the limiting reactant, which is the most important part in doing any yield question, okay? So we now know from this whole process that the bromine is added in excess and the benzene is the limiting reactant. Now that does not answer the final question. The question is asking us what the yield is of bromobenzene, right? So again, the BICPA process doesn't answer that question. It answers what the limiting reactant is. And once you know the limiting reactant, then everything is calculated from that, and you can just ignore the excess reactant. So I'm going to clear the board and we'll go ahead and get to our final answer. So we have 0.35 moles of benzene, and I know now, because I went through BICPA, that this is the limiting reactant. So I need to calculate what the yield is. The yield is another word for the amount of bromobenzene, this thing that is going to come out of this amount of this limiting reactant. So again, by dimensional analysis / unit conversion, my units in the denominator here will be the same as the units in the numerator of the previous term. So I have moles of benzene here. So I'm going to have moles of benzene in the denominator. Is it possible to directly relate moles of benzene to moles of bromobenzene? In other words, can moles and moles touch or be put in the same set of parentheses? The answer is obviously yes. And what numbers go in there? It's the coefficients in the balanced equation. So I've got a 1 next to the benzene, and I got an implied 1 because there's no number written there next to the bromobenzene. So I put 1 to 1. Now, in this particular case, because it's all 1-to-1 across the board, you probably could have answered this and done the last two parts of BICPA a lot more easily than what I did, but I wanted to show you the full process, okay? So you multiply this thing through and you'll discover that if we threw in 0.385 moles of benzene as our limiting reactant, we would end up getting the exact same amount, 0.385 moles of bromobenzene out the other side. So that is the answer to part A, our theoretical yield. Now let's go ahead and move on to part B. In part B, it gives us an actual yield, and the actual yield of bromobenzene is 42.3 grams. So actual yields, just so you know, are numbers that you actually get when you run the reaction. So on a problem that you see on an exam or a problem set or something like that, or a quiz, that number has to be given to you. Now in real life, that is a number that you would actually obtain when you run the reaction yourself in the lab, okay? So it's an actual yield. The theoretical yield is the yield that you get based on calculations that we just did, i.e. BICPA. Make sense? Now the percent yield is essentially a grade for the reaction. Like if you got 5 out of 10 on a quiz, what's your percent on that quiz? It's 5 divided by 10 times 100. Percent yield is the actual yield. That's what you actually got when you ran the reaction, or in this case, if the question tells you what you actually got, in the numerator, divided by the theoretical yield, the amount possible that you should have gotten if everything went perfect, perfect, perfect. That is your total possible score times 100. Make sense? Okay, so our theoretical yield, which we just calculated, I'll write right here so that we keep it all organized in our minds. That's the theoretical yield, and it's in moles. That's how many moles we should have theoretically gotten. It tells us that our actual yield was 42.3 grams. Now I have to make the units match. I cannot put grams up top and moles down the bottom, or vice versa. I have to have them all in one or the other. Now it is possible and totally acceptable to put grams of one thing and grams of the same thing in the same set of parentheses. In other words, I told you earlier that grams and grams can never touch. That is not true if you're dealing with grams of the same thing, the same substance. You could do that. But I prefer to go through moles myself. You could go either way. So what I'm saying is you could convert this into grams and then put it in the denominator, or you can convert this one into moles and put it in the numerator. And that's the way I'm going to go. So I'm going to write down that we have 42.3 grams of our bromobenzene, and I'm just going to write down BB for abbreviation for bromobenzene instead of the formula, because it's going to save me some time. In the denominator, we put the same unit, so grams of bromobenzene. Is it possible to relate grams of bromobenzene to moles of bromobenzene? In other words, can grams of one thing and moles of the same thing touch? The answer is yes, absolutely. So how many grams of bromobenzene are there in 1 mole of bromobenzene? Well, that's the formula weight. Each molecule of bromobenzene has 6 carbons. Each carbon weighs 12, and I'm rounding there to keep things simple. 6 times 12 is 72. Okay, each hydrogen weighs 1, and there are 5 hydrogens, so I'm going to add 5 to the molecular weight. And each bromine there, if you look at the atomic weight of bromine, it's around 80, so I'm kind of rounding there. You add all that crap together, and you end up getting a formula weight of around 157. Okay, the grams of bromobenzene cancel out the grams of bromobenzene. 42.3 divided by 157 on our calculator ends up giving 0.269 moles of bromobenzene. You see that okay? Now again, you can argue with me on the rounding. I think that I'm actually okay for the significant figure rounding. But this is the actual yield that we got in the lab when we ran this reaction, okay? And that was told to us by the problem. So we need to take this actual yield, put it in the numerator, and this theoretical yield, put it in the denominator, times by 100. So I'm going to go ahead and clear a little bit of the board, and we'll do that. So I've got 0.269 moles divided by 0.385 moles, times it by 100 and then round, and you end up getting to around 70%. Hence, the answer to part B is 70%. Isn't that exciting?